Okay. How is everyone today? Good, I hope. Today's the 23rd, I think. Okay, so last time we talked about two things. We talked about equations, and we talked about the things, we talked about equations, and it is the case that a significant task when you're using mathematics is that you want to solve an equation. That's very often the thing you want to do. So we talked about some things you can do with equations, and it turns out that not everything is always okay. So what's something you can always do with an equation and not modify its logical value? Something that's always okay. You can add something to both sides or subtract something. That's always okay. Nothing's ever going to go wrong. What about multiplying both sides of an equation by something? You can multiply both sides by 1. Is it okay to multiply both sides by 3?
Yes.
Yeah.
Not by 3.
But not by 0. Right. So multiplying both sides of an equation or dividing by non-zero is okay. But with 0, you could potentially modify the truth value, the logical value. So as a reminder, because I'm getting a little bit, my teacher sense is telling me that you're not entirely sure about logical value, please remember that equations have a logical value. For example, the equation 3 equal to 3 is an equation that has logical value true. So that's its logical value. There's exactly 2 logical values. What about the equation negative 3 equal 3? What is its logical value? False. And it's a long-standing struggle at the college and university level to make sure that students have separated that there is such a thing there is such a thing as an equation like this one. It's an equation, but its logical value is false. That doesn't mean it's not an equation. It is. It's just its logical value is false. Okay. Fine. Some operations on equations preserve logical value, and others don't. Other operations do not. So we said that multiplying both sides of an equation by 0 may not preserve the truth. Same with dividing. But we actually talked about one more operation near the end of last time that we're going to need to use a lot all the time. And what is that one? Squaring. And these operations come in pairs, the thing itself and its inverse. So adding paired with subtracting and multiplying paired with dividing. So squaring is paired with square roots. So we're very often going to need to square and use square roots, but it may not always preserve the truth, and that's something we're going to have to be looking out for. Okay, so now before we get to the meat of today, I want to remind you of a topic that we talked about like a month ago and hasn't really come up much since then. That is natural domain. Oh, good old natural domain. So the natural domain of an expression is what? Can you remember?
All of the x values
Mhm.
for which the expression.
Very good. So the natural domain of an expression is the set of all inputs for which the expression is defined. So at the present time, the present position in the class, there's two kinds of things that might restrict the natural domain of an expression. What are those two things?
Square root of a negative number
Mm-hmm.
and
And dividing by 0. So restrictions come from those two things. So come from division by 0 and also negative inputs. So what you said was negative inputs to square roots, and I agree, but it's actually a little more general than that. It's negative inputs to what?
Square root. Even square root.
Right, even radicals. Though I agree entirely that in practice, the radical that comes up by far the most is square root. Okay. So, that being said, let's have an example. Please find the natural domain of, how about the square root of 10x plus 2 equal to, I don't know, x over sorry, I'm calculating in my head, plus 10x plus 16. Plus 16? No, that's not what I want. Sorry. I want to say minus 24. Okay. So now, in the first place, I want you to observe that I'm asking something that seems kind of weird, actually, because right here, we just got finished saying the natural domain of an expression is blah, blah, blah. Now, what kind of thing are we looking at here? Is that an expression? It's an equation, right? I want you to see that it's, in a sense, not even the right kind of thing. So in some sense, I want you to see that, well, I kind of asked a question that's nonsense. But, in fact, the interpretation of this is, well, yes, I agree that it's not an expression, but yet this equation is defined for some values and not others. And that's what I want to know. What values could you plug into this equation so that it is defined? But be careful and understand that I'm not asking what values could you plug in such that the equation is true. That's not what I'm asking. I just want to know when it's defined. So if I was asking you to find the set of all inputs such that the equation is true, then what's the name for that? Solve. That's the solution, right? And I'd like for you to look and notice I'm not asking you to solve this equation. So, note. Not asking for solution. We're asking for the natural domain. The reason why I am taking the time to say this is, in the first place, it's an important distinction to be able to understand, oh yeah, this equation could be defined at, say, 100, but it's probably not true there. I'm asking for the natural domain. The other reason is that I'm going to give questions like this as exercises, and someone, maybe even someone who's here, but highly likely someone who isn't, I'm going to give an equation like this, and they're going to try and solve it. And it's going to be beyond the pale. It'll be like impossible to solve. But I haven't asked to solve it. Okay. So what we're going to do is we're going to find the natural domain of the left-hand side. The natural domain of the right-hand side. And then we're going to intersect. Which is to say that we're going to figure out what inputs would be okay for the left one, what inputs would be okay for the right one, and then the natural domain is the inputs which would be okay for both of them. Okay, for the left-hand side, remember the two kinds of restrictions that come up are divisions by zero and negative inputs to even radicals. How many divisions by zero are there on the left-hand side? None, so that's out. We don't even need to consider that. But there is a even radical, because what's the radical number of square root?
2.
2, right? Right, cube root is third radical, square root is second radical. Okay, so then for the left-hand side, what we need to be true is we need, we need the thing being put inside the radical to be greater than or equal to 0. But there's a nice vocabulary word for thing that you put in the other thing. What's the name, the vocabulary word for thing that you put in the other thing? Argument, right? So we need the argument to the square root to be greater than or equal to 0. So 10x plus 2, we need that to be greater than or equal to 0. So now we want to solve this for x. (10x) greater than or equal to negative 2. So x greater than or equal to negative 0.2. And then how could we write this in interval notation? Mm-hmm. To infinity. Which is to say, you know, if you like, negative 0.2 would be fine, all the way to infinity. But anything to the left of that, just out of the question. Okay, the right-hand side. And then let's remember the two kinds of restrictions come from divisions by zero and negative inputs to even radicals. The right-hand side, well, it doesn't have any radicals whatsoever, so that's nice. But does it have any divisions? Yeah, so something could go wrong. Well, let's see. Okay, how can we figure out what could go wrong? Set what equal to 0?
Denominator?
Yeah, okay, so then I'll say it like this. It would be nice if we could factor the denominator. So factoring the denominator, the numerator is all fine. Can you think of two numbers whose product is negative 24 and whose sum is 10? Okay, good. So then x plus 12 multiplied by x minus 2. Now that we've factored it, I hope it's clear that there's two values that are not permissible. What are they?
12
And 2, okay. So then x can't be negative 12. X can't be 2. So you could write this, if you so desired, you could write this in interval notation as negative infinity to negative 12 union negative 12 to 2 union 2 to infinity, which is altogether a complicated way to say all the numbers are fine except those two. So is that the answer to the question? No, right? Because we want to know what's the natural domain of the equation, which is to say we want to know all of the inputs such that the left-hand side is okay and the right-hand side is okay. So we want to actually compute the intersection of these two. So can you do it in your head at this point? Maybe not. Okay, so let's do it on paper. It's fine. So for the intersection, there's 2 sets. There's 3 numbers of interest, negative 0.2, negative 12, and 2. Of those, the one furthest to the left is negative 12. Then the next one is negative 0.2. And then the next one is 2. The absolute position of these is not important, but the relative position is important. So these are in the correct ordering. First that one, then that one, then that one. So this set is everything but those 2 values. And then what is this one? Everything to the right. Yes, including that, including negative 0.2 itself. Okay. And we want to compute the intersection, which is to say we want all the points that have both colors, that are red and green. So how about back here, like at negative 20? Are those red and green? No, they're just green. So that's not going to work. Where's the furthest to the left place where they're both colors? Right there. So at negative 0.2, that's where the intersection begins because you have red and green both. Then you proceed to have red and green points for a while until 2. For that instant, you don't have both colors, and then from then on you have both. So as a result, the intersection you could draw it in the following way. You could say, well, here it is. That's the first place. Negative 0.2. Then we don't have 2. That's out. But all of the rest of this stuff, yes, we have it. So in interval notation, supposing I asked for that, it would be negative 0.2 to 2, union 2 to infinity.
And it's not intersect because it could be either value between the negative 0.2 and 2, or it could be something between 2 and infinity.
Right. So, right. This is blue. It's kind of hard to see. It just looks dark on the screen, but it has to be blue, which means you could either be in this piece or that piece.
Sometimes using the word when we have to identify an intersection,
Mm-hmm.
it confuses me that we use union in the answer. You know.
Right. I get that. So logically, intersection is related to and union is related to or. So what the and-ness comes from that we need the points to be red and green. They must be both colors. So these are the ones that are both colors. And it so happens that the points that are red and green consist of 2 pieces.
So when you're asking for natural domain, it's always going to be one of the two notations that apply.
Well, I'm probably going to ask for all three. I mean, in the end, that's probably what I'm going to ask for. But at any rate, I'll be specific. And if I don't say, then you're free to give any legitimate answer. Good. Okay. So now that means that all of these blue points, these are the points that you're permitted to plug in. Does that mean that the equation is going to be true for all of them? Nah. Nah. The equation is going to be false for most of them. But those are the ones that you could, in principle, plug in. You couldn't possibly even plug in 2. The left-hand side would be fine, right? You plug in 2, 10 times 2 is 20, add another 2, that'd be 22, square root of 22. Well, I don't know it off the top of my head, but it exists. It's a little bit more than 4, a little bit less than 5. However, it's just not even okay to plug in 2 over here, because it causes division by 0. It's just not even okay to even start. Okay. So here we go. Solve x equal to the square root of 5x plus 24. Notably, unlike the previous exercise, the request is to solve. Okay, now on the previous times I've had you solve an equation, it has been the case that there's no radicals in that equation that I want you to solve, and there's no divisions by variables in that equation I want you to solve. As a result, previously, it was just impossible. It was always the case that the natural domain was all reals. Well, that's only because I was keeping us in a walled garden, a safe place, where that couldn't happen, where we didn't need to consider that. But I'm telling you now that we've opened the gate and we're wandering outside now. So, will the natural domain of this expression be all reals? It won't be. As a result, the very first consideration you have to make from now on when you're solving an equation is about the natural domain. So how about the left-hand side? Just concerning just that much. Well, how many divisions are there? None. How many even radicals are there? None. So what's the natural domain? All reals. Which is just, a way to say that, oh, nothing at all could go wrong on the left-hand side. What about the right-hand side? Right. No divisions, so that's nice, but there is an even radical, so we've got to deal with it. As you say, the argument needs to be greater than or equal to 0. So now we want to solve that for x. So we need 5x to be greater than or equal to negative 24. So x needs to be greater than or equal to negative 24 over 5. And because it's going to come up later, I'm going to go ahead and write that as a decimal. So x is greater than or equal to, well, 4, and then 4/5, so 4.8, negative 4.8. So what we're saying is that, well, could you plug in x is negative 2 into the equation?
Yes.
Yeah, you could, because it's more than negative 4.8. 5 times negative 2 is negative 10, and then add 24, that's 14. I don't know the square root of 14 off the top of my head, but it is a number. Okay. So writing this in interval notation, that'd be negative 4.8 to infinity. As a result, what's the natural domain of the equation? That one, right? Because, well, there's just no restriction on the left-hand side. The reals intersect that is that. If you like. You know, sort of really forcing the issue and writing it like this. The left-hand side requirement and the right-hand side requirement. Wait, what happened there? I'm not even sure. Ah, well, maybe it's because the 8 kind of looks like an infinity. Negative 4.8 to infinity. That means that any solution that anything that we say is a solution needs to be in here. What I want you to see is that it is in some sense reasonable for you to tell me 5 could be a solution, or and 10 might be a solution because they're in there. But if you were to try and tell me that negative 7 is a solution, that's wrong in sort of a categorical way, like saying that you know, this is a delicious red apple. And then I say, no, not really. And then you say, well, it's red. Okay. So, good. So now we're going to perform some algebraic steps. So x is square root of 5x plus 24. We want to solve for x. The problem, sort of from a high level point of view, that we need to overcome is the fact that there are x's which are inside a radical and also x's which are outside of the radical. So sort of from a high level point of view, we need them all to be out in order for us to come to the answer. So we need to get x's out of the radical. So in particular, in some sense, the right-hand side is the problem side. What do we need to do to get the x's out of the radical on the right-hand side? We want to square both sides. Because, well, we want to square it so that the radical will go away. But what you do to one side you must do to the other side. But so you're telling me that we're going to take this equation. We're going to take the left-hand side and we're going to square it. And we're going to take the right-hand side and square it. But wait, didn't we take a bunch of time last lecture and very carefully indicate that that's not really an excellent thing to do all the time? Yeah. Yes?
But in this case, it's like the only thing that you do.
Right.
There's not really any other way around. It's
Right.
like the only way to get rid of it is to do the opposite. It's good.
Okay, good. So what I want you to remember is that this is well, it's not that it's not permitted. It's that it is something that you do with care, right? Like a chainsaw can be used safely. They really can be. But they can also cut your leg off, right? So we're going to mark this as, oh, this was a place that we had to do something questionable. So we're going to remind ourselves that squaring may not preserve truth, may not preserve logical value. Okay.
Now, I also am, I feel like I've learned enough at this point to say I need to start thinking about absolute value.
Okay, let's discuss that. So the left-hand side could be written as x squared. Then, yes, here the question is what comes of the right-hand side? Is it absolute value?
Something of absolute value of something.
And unfortunately, nope, there's no absolute value. At which point, you would, in my opinion, fairly say, now wait a second.
Shake my head.
You've
Right.
you've harped on that
Yeah.
all semester, and now you're saying no? Well, let's look at it carefully.
I'm going to push my button on you.
click the button. So, this is the one that I've been saying all semester. If you take a y, and then you square it, and you follow that up by a square root, which is to say, square first, then square root. What do you get?
Absolute value.
You get the absolute value of y. And I stand firm on that. That is still the case and will always be the case. But there's two things going on there. And the thing that's occurring first is the squaring. You take the y and you square it, and you follow that up with square root. What if we reverse the order of the things that are occurring? What if we take a y, compute square root first, and then follow that up with a square? What if you do that? You just get y. Now, why do you just get y? The reason is because, well, consider what, in this operation, what's occurring first? Square. You're doing the square root first. And yes, I agree entirely. Because we're working under the assumption that this is actually defined, it is the case that y is greater than or equal to 0 because we're putting it into the square root. Because you're putting y into the square root, it is necessarily greater than or equal to 0. So that means that no, you don't like it?
No, the only thing I just go back to the first one and say, well,
Mhm.
why isn't it the case that we are assuming that y
Mhm.
squared,
Mhm.
the first one,
Mhm.
is greater than 0?
Okay. Because do you agree that we could take a negative 3 and we could square it? What do you get?
9.
You get 9. And then we could follow that up with square root. What do you get? 3. That one first, then that one, and furthermore, we could just write that as absolute value of negative 3. Whereas, can you agree that if we were to take the negative 3, and the first thing that was requested was square root, what would we have to conclude?
Can't do it.
It can't do it, right? It just blows up. So, you know, boom. Universe exploded. So what I'm saying is that by virtue of the square root happening first, it is necessarily true that you didn't put something in negative. So they're definitely related, but I'm trying to stress for you that the order matters. And the one we've been talking about all semester is this one. And here's a different one. So you need to know that absolute value only applies to that one. Okay. Well, okay. That being said, of these two possibilities, which one did we do from here to here? The new one, right? So from here to here is that one. Okay. So now I'm going to take these three terms, the one on the left-hand side and the two on the right-hand side, move them all to the left-hand side. And we get x squared minus 5x minus 24 is equal to 0. Wow, it's a quadratic equation. What a coincidence that That's happened. So we can solve every conceivable quadratic equation because we know the quadratic formula. So in principle, we could just jump right in with the quadratic formula, but perhaps there's an easier way?
Let's see.
Square difference
Can you think of two numbers whose product is?
of negative 8 and 3.
There you go. So x plus 3 multiplied by x minus 8 equals 0. So now we have, it is the case that the product of two things is 0. So either the first thing is 0 or the second thing is 0. So that has to be the case. So the possibilities split into 2, so that it might be the case that x plus 3 is 0. It might be the case that x minus 8 is 0. Then each one of these can be solved individually. So x is negative 3, or x is 8. So now is this the answer to the exercise? So, there's something called Bedridge's law of headlines, where you read a story, a news story with a headline that's a question, a yes or no question. The answer is like uniformly no, right? Is this the end of the world? No. Is that political event going to result in the destruction of our beloved republic? Nah, probably not. No, right? So then when I ask, is this the answer to the exercise, the answer is no, right? Of course it isn't. There's two things that might have gone wrong. So in the first place, is it the case that every number is in the natural domain? No, right? I mean, there's a lot of them that are just not in there. So we're going to need to check, is it the case that these candidate solutions are in the natural domain? Furthermore, negative 3 and 8, they are solutions to this equation. There's no dispute. But that's not the equation that we were asking about, right? How did we get this equation?
We did something.
We squared both sides. You know, that's the chainsaw, right? There's a legitimate way to use it and an illegitimate way to use it. As a result, because we solved this equation, but on the way to this equation, we did something that might not have preserved the logical value, that means that everything here is under suspicion now, which means everything needs to be checked against both conditions. We need to check this. Is it in the natural domain? And if so, does it solve the original equation? And same thing for that one. So now we make our checks. Checking x is negative 3. Is it in the natural domain? Yes. Okay, because, well, it's more than negative 4.8. Does it solve the original equation? We know that it solves this other one. Let's check. Let's plug it in. The original equation is right there. So plugging in x is negative 3. Negative 3 equal to square root of 5 multiplied by negative 3, add 24. Well, 5 multiplied by negative 3 is 15. Add 24 is 9. So negative 3 equals square root 9. And what's the square root of 9? 3. Well, how about it? What's the logical value of this? False. Therefore, what is our conclusion about this candidate? It's not a solution. Okay. Let's check the other candidate, x equal 8. So in the first place, is it in the natural domain? Yes, it is. Okay. Besides being in the natural domain, does it satisfy the original equation? Well, there's only one way to confirm or deny it. Let's plug it in. 8 equal to square root of 5 multiply 8, add 24. 5 multiplied by 8 is 40, add 24 is 64. 8 equals square root 64. 8 equal 8. Well, what's the logical value of that? It's true. Therefore, what is our conclusion about candidate x equal 8? It is a solution. Therefore, our conclusion is that the only solution is x equal 8. Okay. So wait a second. All right. I'm a human being like everyone, and I think we can all agree without dispute or comment that, well, this was a bunch of work right here, and not doing work is better than doing work. And I think we can all agree on that. Why did this come up? Did it have to come up? It did have to come up. There was no way to avoid it. And I promise you, if there were a way to avoid it, I'd show you, for the simple, selfish, expedient reason that the less work you submit, the less I have to grade. Right? So why did it come up? Exactly this. Is that equation true? It is not. What if you square both sides? It is. That's where it came from. So this this whole issue, this happened because of asterisk. Happened because of this. And that equation isn't true, but it is true if you square it. So, good. Any question about this? So, that being said, I want to make sure that you understand solving an equation now has the following kind of structure. Before, when we were solving, like, 3x plus 4 is equal to 8. Well, that didn't have any divisions by variables in it. It didn't have any radicals. That was a really tame equation. It was like we were at the petting zoo with the goats, Now we're at the part of the petting zoo where you're petting the tiger. You got to be more careful. So the way it works now is that when solving an equation, I suppose you probably have to be pretty careful with goats too, to be honest. Okay, but when solving an equation, you first compute the natural domain. Then you perform your algebraic steps. The conclusion of the algebraic steps will be a list of candidates. In the previous exercise, there were 2 candidates. in practice, there could be 0 or more candidates. Like there could, in principle, be 48 candidates. Never that many, I promise. But in principle, it could happen. 3. You exclude candidates from 2 which are outside of 1. Which is to say, you find a candidate, you have to exclude anything that's not in the natural domain. And 4, you exclude candidates from 2 which don't satisfy the original equation. Now here's the thing, is that this last step is only necessary when an operation which does not preserve truth value, logical value. Logical value is used in step 2. So here's the flat truth of it all, is that this semester so far, until now, it has been the case that every equation that we solved, the natural domain was all reals. And furthermore, it has been the case that it was never necessary to use an operation that might modify the logical value. As a result, solving equations up to now looked like there was only one step, that step. But that is not the case anymore. From now on, you'll need to find the natural domain, then do the algebraic steps that you know and love. Then you'll need to start excluding candidates on these bases. Good. Any question about that? Okay. I hope y'all have a nice weekend.